In 1941, Chrysler took 5 regular car engines, bolted them together in a circle, and told the U.S. Army it was a tank engine, 30 cylinders, 21 liters, 5 carburetors, 5 distributors, 5 crankshafts, all feeding into one central gear. They called it the A57 Multibank. The Army called it a nightmare. The British called it a lifesaver. So here's the situation. It's mid-1941. America hasn't officially entered the war yet, but everyone with a pulse knows it's coming. And the country has a problem that nobody in Washington wants to talk about publicly. In 1939, the entire United States Army owned 66 medium tanks. 66. The whole country. For context, Germany had just rolled through France with over 2,000 panzers, crushing the most powerful army in Western Europe in 6 weeks. America wasn't behind in the tank race. It wasn't even in the race. The Army's existing tanks were a generation old, undergunned, under-armored, and built in numbers that wouldn't fill a decent parking lot. The tank the Army had been building, the M3 Lee, ran on a Continental R975 radial engine, originally a Wright aircraft engine, license-built by Continental Motors for ground use. Decent power, around 400 horsepower, air-cooled, 9 cylinders arranged in a radial pattern and already in mass production. It had been powering light tanks since '39 and was the natural choice to scale up. The problem was that every aircraft manufacturer in the country also needed radial engines. Bombers needed them. Fighters needed them. Trainers needed them. Transport planes needed them. The Army Air Forces and the Army Ground Forces were locked in a bureaucratic knife fight over who got priority on engine production. Continental would eventually build over 53,000 R975s for armored vehicles alone, but in '41, that output was still theoretical. The shortage was real, and it was now. President Roosevelt had announced a production target calling for 120,000 tanks for the Allied war effort. 120,000. Even if that number was aspirational, even if the real figure ended up being half that, the math on engine supply didn't work. Not with one engine type. You can't win a two-front war if your tanks and your planes are fighting each other for parts before they ever see the enemy. Something had to give. The Army needed alternative engines, and they needed them yesterday, not after a clean sheet design and a nice prototype phase. Now. So they went to Detroit. Because in 1941, if you needed something manufactured in impossible quantities on an impossible timeline, you called the American automobile industry. These were the people who had figured out how to build a car every minute. If anyone could solve a production crisis under pressure, it was them. General Motors offered to strap 2 of their 671 supercharged truck diesels together on a common crankcase. Practical, straightforward. The twin diesel weighed more than the radial, but had excellent torque characteristics. Tanks powered by it handled better at low speeds, and the Soviets loved them. Ford started working on a massive 1,100 cubic inch V8, the GAA, purpose-built for tanks from the ground up. Ambitious but conventional in concept, and when it was finished, it would become the Army's preferred power plant. But it wasn't finished. Development takes time that the war was not willing to give. And then there was Chrysler. Chrysler's president was a man named Kaufman Thuma Keller. Everyone called him KT or Katie. Nobody used his first name. When William Knudsen, Roosevelt's newly appointed Director of National Defense and former president of General Motors, first called Keller on June 7, 1940, and asked if Chrysler could build tanks, Keller's response was immediate and completely honest. He said he'd never seen one of those things, not a polished corporate deflection, just a fact. He'd spent his entire career building automobiles, but he said yes anyway, without hesitation. The board of directors had given him authority to make such decisions 3 months earlier. The next day, Keller assembled a team. By the end of that week, the team had traveled to Washington, inspected prototypes in Illinois, and started studying 186 pounds of blueprints. Within weeks, Chrysler signed a contract to build 1,000 M3 tanks at a new factory that didn't exist yet, on land that was still farmland, for a price of $33,500 per tank. Keller charged the government $4 to design the factory buildings. $4. That factory became the Detroit Tank Arsenal. 113 acres of former farmland in Warren, Michigan, 17 miles from downtown Detroit, designed by Albert Kahn, the legendary industrial architect responsible for half the factories in the Motor City. Its walls were 3 feet of reinforced concrete in critical areas, built to survive aerial bombardment. Chrysler built the plant so fast that the first M3 Lee tanks rolled off the assembly line before the exterior walls were even finished going up. During the brutal Michigan winter of 1940-41, they brought a steam locomotive inside the partially completed building just to keep the workers warm. There was no heating system yet, just a locomotive sitting on the factory floor, burning coal, while men assembled 30-ton war machines around it. Now the Army came back to Keller with a harder question. They didn't just need tanks. They needed tank engines, a lot of them, fast. And they needed them built with existing tooling, because there was no time or industrial capacity to design and manufacture new machine tools. Every weapons factory, shipyard, and aircraft plant in the country was already fighting over the same equipment. This is where the story turns. Chrysler's executive engineer Harry Wilson and his engine design chief, Mel Carpentier, looked at the problem and came up with a solution that was either brilliant or completely insane. They'd probably have told you it was both. Chrysler had been building their 251 cubic inch flathead inline 6-cylinder engine for years. It powered Plymouths, Dodges, and Chrysler sedans, rolling off showroom floors across America. It was a reliable, thoroughly understood, boringly dependable car engine. The tooling was mature, the supply chain was established and running. The workers on the production line could build these engines in their sleep. One of those engines made about 85 horsepower. A medium tank needed around 400. So they did the math. 85 times 5 equals 425. Close enough. Then they did something that nobody in the history of engine design had attempted at this scale. They took 5 of those car engines and arranged them in a star pattern around a massive cast-iron crankcase. 2 engines on the bottom angled just 7.5 degrees above horizontal. 2 more above those above, tilted at 27 degrees, and one sitting straight up on top like the point of a crown. 5 separate crankshafts, each fitted with a herringbone-cut drive gear, all meshing with a single central sun gear that drove one output shaft. 5 engines, 5 sets of pistons firing in coordinated sequence, 5 streams of exhaust, all harnessed to turn one gear, 30 cylinders, 1,253 cubic inches of total displacement, 20.5 liters, bore of 3.4375 inches, stroke of 4.5. The official designation was a 57. The unofficial nickname, coined by Army Ordnance personnel who had to deal with the thing, was the Egg Beater. The complete engine assembly, with radiator, cooling fan, and clutch, weighed 5,244 pounds. That's over 2.5 tons, just the engine package. The Ford GAA Vi-8 that the Army actually wanted weighed about 1,560 pounds, dry. The Multibank weighed more than 3 times as much for roughly the same power output. But it existed, right now. It used parts already rolling off civilian assembly lines, and it could be in full production before Ford's engine was even ready for tank installation testing. In wartime, existing beats elegant every single time. The speed of development was staggering even by wartime standards. The initial discussion about the engine concept happened in mid-1941. By November, test engines were ready for tank installation. The first M3A4 tanks rolled off the line with production A57 engines on June 3, 1942. 9 months from concept to a tank you could drive. For an engine this complex, with 5 independently geared crankshafts feeding a central sun gear, that timeline borders on absurd. The engineers at Chrysler weren't just building an engine. They were inventing a new category of power plant while simultaneously debugging it, tooling for it, and training production workers to assemble it. Here's the part that doesn't make it into the feel-good wartime production stories. The Army didn't want this engine. From day one, the brass considered the Multibank a temporary fix, a desperate measure born from a desperate shortage, not a real answer. They tested early A57-powered tanks in the California desert in October of 1942, 5 M3A4s and 5 M4A4s, and the results were brutal. The engines overheated relentlessly, water pumps failed, generators died. The radiator fouled with grease and dirt because the seals around it weren't adequate for desert conditions. The engine had 5 individual belt-driven water pumps, 1 per bank, and those belts snapped with depressing regularity. The carburetors were a disaster of their own. Each of the 5 Carter TD1 single-barrel carburetors was mounted near its respective engine bank, connected to a common air cleaner by intake pipes of different lengths and shapes. The result was unequal fuel distribution across the banks. Some ran rich, some ran lean. The engine never quite breathed evenly. Metal vanes were added to redirect airflow. It helped. Not enough. The engine compartment was so cramped that mechanics could barely reach anything useful. Routine adjustments on the 2 bottom engine banks, the ones angled almost horizontally, meant contorting yourself into positions that would challenge a contortionist. If anything major went wrong, a bad piston, a cracked valve, a seized bearing, even a significant vacuum leak, the entire 5,200-pound assembly had to come out of the tank. Chrysler anticipated this and built massive lifting eyes into the central crankcase because they knew full extraction was going to be a regular event. That's not optimism. That's engineering realism from people who understood their own creation. The Army's Armored Council was blunt. The M4A4, the Sherman variant housing the Multibank, was declared unfit for American combat units. Too complex, too heavy, too hard to maintain under field conditions. The Army wanted Ford's V8, or failing that, the Continental radial they already knew. Every M4A4 was restricted to training use inside the continental United States. Keller was warned that the engine was a stopgap and might not be ideal for the duty. He already knew. So what do you do with 7,500 tanks that your own Army refuses to fight with? You give them to the British. If you're enjoying this, hit subscribe. We cover stuff like this every week. Okay, back to it. Under the Lend-Lease program, nearly every M4A4 Sherman built at the Detroit Tank Arsenal was loaded onto a transport ship bound for England. The British designated it the Sherman 5. And here's where the story pivots on its axis, because the British didn't just reluctantly accept these American cast-offs. They came to depend on them. Chrysler, to their lasting credit, didn't ship the tanks and walk away. They sent technical representatives across the Atlantic, engineers who knew the Multibank inside and out, who could diagnose a misfire by sound and trace a fuel distribution problem by intuition. These tech reps embedded with British maintenance crews and taught them every quirk and vulnerability the engine possessed. Chrysler also probably established several rebuild depots in England, specifically for A57 power packs that needed major work. And back in Detroit, the engineering team kept improving the design based on every field report that came back. The 5 individual belt-driven water pumps were eliminated entirely. In their place went a single centralized gear-driven pump that fed coolant to all 5 banks through individual channels. No more belts to snap, no more mismatched pump failures. The carburetors were relocated from their scattered positions near each engine bank to a grouped arrangement on top of the engine, where mechanics could see and reach all 5 without performing gymnastics. This simplified the throttle linkages, cleaned up the air cleaner system, and turned routine carburetor adjustment from a 2-hour ordeal into a manageable job. A Chrysler engineer named Bert Dickinson eventually cracked the persistent fuel distribution problem that had plagued the engine from the start, redesigning flow paths until all 5 banks received properly balanced fuel charges. The engine blocks needed modification too. These were passenger car engines designed to sit level under the hood of a Plymouth. Nobody had originally planned for them to operate tilted at angles inside a tank. The water jackets in the lower banks had to be re-drilled to improve coolant circulation when the blocks were inclined. The generator was relocated from the engine to the fighting compartment, where it ran off the main drive shaft, eliminating a chronic failure point and freeing space in the packed engine bay. Stellite-faced sodium-cooled exhaust valves replaced the originals for better heat resistance. Chrome-plated top piston rings improved durability under sustained load. Now let's talk about how this thing actually worked, because the engineering, once you see the logic, is elegant in its brute force way. The central crankcase was the structural spine of the whole assembly. 5 Chrysler 251 flathead 6s bolted to it at their prescribed angles, each one essentially a complete engine minus its own oil and water systems. The flathead architecture, with valves seated in the block rather than in an overhead arrangement, made these engines more compact vertically. That mattered enormously when stacking 5 of them inside a confined hull space. The compression ratio was 6.2 to 1, conservative by any standard. Your average 1942 family sedan ran about the same. But conservative was the entire point. A 6.2 to 1 ratio meant the engine ran contentedly on 80-octane gasoline, the standard military ground fuel available everywhere from North Africa to Normandy to Burma. No need for the high-octane aviation fuel that the R975 originally demanded. In a global war where fuel crossed oceans in tanker convoys, dodging torpedoes, burning the cheapest available gas was a strategic advantage that never showed up on a spec sheet but showed up in every supply officer's daily reality. The gear train was the real mechanical achievement. 5 herringbone-cut drive gears at the crankshaft outputs meshed with the central sun gear. Herringbone gears, also called double helical gears, generate almost no axial thrust and minimal backlash, meaning power transfer from 5 independent crankshafts to one output shaft happened smoothly, without the vibration and shock loading that would shatter a lesser arrangement. Each engine bank drove at 3,100 revolutions per minute, while the output shaft turned at 2,600, a modest gear reduction that added useful torque at the cost of some peak speed. Net output settled at 370 horsepower at 2,400 RPM, with a gross figure around 425. Torque was where the multibank earned its keep, 1,060 pound-feet gross. That low-end pulling force was exactly what a 34-ton tank needed to climb a hill, cross a muddy field, or accelerate from a standstill without bogging down. The Continental Radial made similar peak horsepower, but had to be revved much harder to find it, which accelerated wear and shortened engine life. And then there's the feature that changed minds in combat: redundancy. Each engine bank was mechanically independent. If one bank seized from shrapnel damage or mechanical failure, the other 4 continued driving the sun gear without missing a beat. If 2 banks went down, you still had 60% of your power plant pulling. Chrysler ran a full-page advertisement in the February 1944 issue of Popular Science, claiming the tank could still move with 12 of its 30 cylinders knocked out, 40% of the engine destroyed, and the tank still rolling under its own power. In combat, where a single shell fragment punching through the engine deck could kill your mobility and leave your crew stranded in a killing zone, that redundancy wasn't a marketing claim. It was a survival feature with a body count it prevented. The oil system used twin pumps in the central crankcase. A scavenge pump pulled spent oil from the engine sections and transferred it to a remote reservoir. A pressure pump drew clean oil from that reservoir and distributed it under high pressure to all 5 banks. Total capacity was 32 quarts, 8 gallons. The engine consumed oil steadily and predictably, and letting the level drop was a mistake no competent crew made twice. Despite every development problem, despite the Army's rejection, the A57 Multibank quietly became one of the most reliable Sherman engines in active service. The data was unambiguous. In comparative trials through late 1943 and into 44, the M4A4 required an average of just 45 hours of engine maintenance over the test period. The M4A3 with Ford's GAA-V8 needed 110. The M4A1 with the Continental Radial took 132. The diesel M4A2 needed 143. The engine everyone mocked needed less than half the maintenance of the engine everyone wanted. Not by a slim margin, by a factor of 2 or 3. Later, dedicated testing of 4 M4A4s from October 43 through February 44 confirmed the trend. One engine needed major work after 339 hours. The other 3 ran for 400 hours with less than 10% power loss. For a power plant the Army had dismissed as an overcomplicated liability, those numbers were a quiet and thorough vindication. By D-Day, June 6, 1944, the M4A4 was the most common Sherman variant in British service. The majority of British tanks rolling onto Normandy's beaches were powered by the egg beater. The Sherman 5 became the preferred hull for conversion into the Sherman Firefly, the variant mounting the British 17-pounder anti-tank gun in place of the standard 75mm. The Firefly was the only Allied tank in Normandy that could reliably penetrate a Tiger's frontal armor at combat distance. The Germans learned to spot Fireflies by their longer barrel and targeted them first. A lot of those Fireflies rode on the back of 5 Chrysler car engines. The Polish 1st Armored Division entered Normandy equipped primarily with Sherman 5s and Firefly VCs. Canadian, South African, New Zealand, Czechoslovak, Indian, and Chinese armored units all fielded M4A4s at various points during the war. It served with more nations than any other Sherman variant. The tank the U.S. Army rejected became the most internationally distributed Allied tank of the conflict. Production of the A57 ran from April 1942 to September 1943, 17 months. Chrysler built 9,965 multibank engines in that window. 7,500 went into tanks, the rest were spares. The M4A4 quickly replaced the short-lived M3A4, with the first M4A4 completed on June 30, 1942. From that point, the arsenal was producing multibank Shermans at a pace that strained the supply of ship transports to carry them overseas. The Detroit tank arsenal, through the entire war, produced 22,234 tanks, roughly a quarter of all American tank production. In December of 1942, 5,000 workers set an all-time monthly record by turning out 907 Sherman tanks in 30 days. Think about that number. 907 tanks, 1 month, 1 factory. The German war machine, with all its engineering prowess and industrial capacity, couldn't match the output of a single Chrysler plant in Warren, Michigan. Chrysler alone outproduced the entire Third Reich in tanks during the war years, and Keller's executive team did it for a symbolic salary of $5 per year. Every senior Chrysler executive took that token payment for the duration of the conflict. When production costs came in under estimates, Chrysler wrote the U.S. government a rebate check for $7.9 million during a war while building tanks. They gave money back. The company also accepted top-secret contracts beyond tank production, including work on anti-aircraft guns and, in 1943, a classified contract to electroplate miles of tubing for the K-25 gaseous diffusion plant at Oak Ridge, Tennessee. That was part of the Manhattan Project. Chrysler was building tank engines and helping develop nuclear weapons at the same time. Keller never said no to anything the government asked. After the war, the A57 became an orphan almost overnight. American car parts for a mid-40s Chrysler Flathead 6 weren't available in post-war Europe, and the engineers who understood the engine went home to civilian life. Chrysler's support network for the Multibank evaporated as the company pivoted back to building sedans and station wagons for the booming post-war consumer market. Most surviving M4A4s had their multibanks ripped out and replaced with Continental radials or GM diesels. The engine that earned the respect of British tank crews across 3 continents was simply too exotic to maintain without the company standing behind it. After the early 1950s, finding someone who knew how to tune 5 synchronized carburetors on a tank engine built from Plymouth parts was essentially impossible outside of a few Chrysler retirees. The Detroit tank arsenal itself survived the war and kept building. It produced M47 Pattons for the Korean War, M60 Pattons through the Cold War decades, and eventually the M1 Abrams. In 1982, Chrysler sold its defense division to General Dynamics for $348 million. The plant finally closed in 1996. The site is now partly civilian use, partly home to the U.S. Army's Tank Automotive and Armaments Command. A Michigan historical marker stands where Keller's factory once turned farmland into the arsenal of democracy. Today, an M4A4 with a running original A57 is extraordinarily rare. A handful exist in Europe, mostly Firefly conversions maintained by dedicated collectors who treat the engine with the reverence usually reserved for museum pieces. The Tank Museum at Bovington in Dorset has a complete A57 and acquired a second unit without its radiator in 2019 from the UK Defence Academy at Shrivenham. Both sit in the Conservation Centre, not currently on public display. The Imperial War Museum at Duxford has another. The Walter P. Chrysler Museum in Auburn Hills, Michigan, displayed a beautifully restored example for years, giving visitors their only chance to see this improbable engine up close. That museum is permanently closed now. The engine that helped win a war sits in storage, waiting for a home. If you think about it, the A57 tells you something about how wars are actually won. Not always with the best equipment, not with the most sophisticated engineering, but with whatever you can build fast enough and in large enough quantities that it makes a difference before the window closes. The German Tiger tank was a masterpiece of armored engineering. It also broke down constantly, took forever to build, and Germany made fewer than 1,400 of them during the entire war. Chrysler built nearly 10,000 multibank engines in 17 months from car parts. The Tiger crews had to return to the factory for servicing. The Sherman crews fixed theirs in a field and kept fighting. The multibank was an impossible answer to an impossible question, designed by car engineers who'd never built a tank engine, approved by a president who'd never seen a tank, rejected by the army that commissioned it. It was ugly, heavy, and by every rational peacetime measure, it shouldn't have worked. It worked. It carried Allied crews across 3 continents, powered the Fireflies that killed Tigers, and then vanished when peacetime decided simplicity mattered more than battlefield survival. Sometimes the craziest solution is the one that saves your life. Chrysler looked at 5 ordinary car engines and saw a way to win a war. And there you have it. 5 engines, 30 cylinders, one of the strangest power plants ever mass-produced. If you've seen an A57 in person or worked on one, drop it in the comments. I want to hear that story. And if you made it this far, subscribe. We do this every week.